way that we saw how to make carbon-carbon bonds in OChem 1 was actually SN2 with cyanide. I don't think anybody mentioned this. Cyanide is a carbon nucleophile because it's the carbon that holds that negative charge just like the alkyne. And when I react it with an electrophilic alkyl halide, I do create a carbon-carbon bond. And in both of these cases, we're not showing the counter ion, but if we did, we would say typically this is sodium. I saw a textbook once that said this was a covalent bond between carbon and sodium. And they didn't list any explanation for that because it, based on every piece of knowledge you've been taught up until this point, should be labeled as ionic. So unless it behaves somewhat covalently, somehow by bond strength, then maybe we could say that it is a covalent bond, but I would encourage you to think of it as ionic. Then the Diels-Alder reaction. And the Diels-Alder is such an interesting application of carbon nucleophile versus carbon electrophile. Oftentimes in the Diels-Alder reaction, we slap on electron withdrawing groups to the dienophile. And we know better what electron withdrawing groups are now. Carbonyls, cyanos, nitriles, nitro groups, which pull electrons away from this region and make it easier for the diene to attack that position. Carbon nucleophile, carbon electrophile. But it gets even more confusing than that because now the dienophile also acts as a carbon nucleophile to the diene, which acts as a carbon electrophile. Boy, I can't say those words too many times and expect you to know it still. So, can someone define nucleophile? Sometimes negatively charged.
All the ones we've seen have been, right?
Exhibit A. No. Alcohols and water in SN1 reactions are neutral, but they are the nucleophiles. They take on a positive charge afterwards. So it is true that a nucleophile will typically become more positive after it has acted as a nucleophile. Exception here. Say that again?
It's the group that attaches to a molecule.
A group that attaches. Yeah, but is it attached because it received electrons from the group and now it's attached, or because it gave electrons? Nucleophile gives electrons. Nucleophile gives electrons, electrophile. Okay, what am I looking at here? Nucleophile or electrophile? Electrophile. It will take electrons from the nucleophile. What am I looking at here? Nucleophile. Good. Once we got into OChem 2, we learned about the Friedel-Crafts alkylation and acylation. And we've discussed this in some depth. This is where the aromatic ring attacks either this has a name, but I always forget it. I like to call it the carbonyl cation because this is the result of that carbonyl carbon, the acid chloride. And the oxygen is stabilizing the resonance. Or from a carbocation. Which reminds me, I had an interesting conversation today with a student talking about all the different ways that we can make that carbocation. We know that a tert butyl halide can make that carbocation when the chlorine leaves. We also saw that if I form a primary carbocation adjacent to that tertiary carbon, I can do a hydride shift and also make that carbocation. But all of our reactions from OChem 1 with alkenes also apply, because alkenes as bases will form the most stable carbocation. 3 different ways, 3 very different starting materials, all lead to the same carbocation, and this is electrophile or nucleophile? Electrophile, meaning the ring is acting as nucleophile. The ring here uses its pi electrons and attacks, becomes more positive, takes on that positive charge in the resonance forms. And do we consider this electrophilic aromatic substitution or nucleophilic aromatic substitution? Lily? Electrophilic. Because although the ring is the nucleophile, it's being substituted by an electrophile. Okay, those are our ways to make carbon-carbon bonds. How important do you think it is to an organic chemist to be able to make carbon-carbon bonds? Yeah, pretty important. If you are starting from a small molecule and you need to make a larger molecule, there's a good chance you're going to need to extend your carbon-carbon chain at some point. So you will need to introduce both carbons that are nucleophilic and carbons that are electrophilic. And I didn't do this, but I should have. I'm going to go through and label everything that was nucleophile and electrophile. Unfortunately for this one, it was both. I point that out to you because I want you to be mindful as we get into this next unit about what is a good nucleophile, what is a good electrophile. It's not always obvious. It's not always negatively charged. Okay. Now we introduce organometallics. Which is pretty self-explanatory, right? Organos bonded to metallics. So we represent this as Rm. In fact, the worksheet that I'm going to hand out to you guys right now and also upload to Canvas right now is titled Rm and ROH. Rm stands for? Thank you, Elliot. Organometallics. Okay. In the same way that some people say the carbon-sodium bond can be seen as covalent, some of these other bonds are going to be drawn covalent despite how confusing they might seem to think of them as covalent. And I want to give you guys an example even of one that we can prove behaves ionically. Okay, the metals that we're going to deal with are magnesium and lithium. And that may surprise you. I know it surprised me when I was first learning about this. Because it seems like such an odd selection. You're welcome. Not in the same row, not in the same family. Thank you. So we'll start with this organohalide. This is our starting point. Typically, bromine or chlorine. It's not impossible to do this with iodine. In fact, one of the organometallics works best with organoiodides, but Doesn't really matter, and I'm going to be using bromine and chlorine the most. Can we describe the substitution of that alkyl halide? Do you guys agree? Is it allylic? Is it vinylic? Is it aryl? No, this is just alkyl. But that does not limit this. So we could also show this. Also. How many ways do I have this coming down? Allylic, vinylic, and aryl. So to give you an example of what that means, here's allylic, here's vinylic, and here's aryl. Ooh, okay. This is cool. Very rarely do we see common characteristics across all types of alkyl halides. It doesn't just have to be an sp3 hybridized carbon. It could be sp3 adjacent to sp2, allylic. It could be an sp2 hybridized carbon. It could even be an aromatic carbon. Now, some of you might be saying, can I get it down to an sp hybridized carbon? I've had that question before. I've never seen an sp hybridized carbon to a halogen. That is an alkyne bonded to a halogen. Not saying it doesn't happen, but it's just not common. Let's look at the reaction that runs to the right. We will treat this alkyl halide with elemental magnesium. You might represent that as Mg. Notice the charge. Zero? No charge. You can even write that if you want to, Mg0, to explicitly show that this is not magnesium ion. This is the magnesium you dig out of the earth. And the product that we form, Mgx. Now this is roughly equivalent to, so I'm going to show this as equal but a little bit wiggly, a carbon anion, a magnesium ion 2+, and a halide ion, a halide anion. What has happened to magnesium chemically? Can you describe it? It's been oxidized. Oxidation is loss of electrons. Magnesium has gone from 0 to 2+. That's more positive. It needs to lose electrons to become more positive. If magnesium has been oxidized, what has been reduced? The halogen has not been reduced. The carbon has been reduced. How can we prove that? Sorry? Because of the negative charge on the carbon. But then Max's point still kind of stands, which is, hasn't the halogen also been oxidized?
There's a lone pair in the carbon and not bonded to anything, so it gets electrons.
Can we say that the halogen also has a new lone pair that's not bonded to anything? It had 3 lone pairs here. Now it has 4. Hasn't it been reduced? It was already at -1. This is not just counting electrons in the vicinity of the atoms, it's assigning oxidation states. So this is not something we get into deeply, but oxidation states are not hard to assign. In fact, in my opinion, they're a little bit easier than doing formal charge, but very different from formal charge. Oxidation state is equal to the formal charge of a monoatomic ion. Here's a monoatomic ion. Its charge is -1. Its oxidation state, -1. Magnesium, monoatomic ion, 2 plus formal charge, oxidation state, 2 plus. In bonded systems, we can look at the difference between bonds to things less electronegative that the atom in question steals electrons from, and bonds to things more electronegative that the atom in question loses electrons from. 2. Carbon here is bonded to 2 carbons with equal electronegativity, no impact on the oxidation state. Carbon is bonded to a halogen, which is more electronegative than itself. Carbon loses electrons to the halogen. Should I say that the carbon receives a +1 oxidation state or a -1 oxidation state as a result? It's losing electrons to the halogen. It should get more positive as a result, +1. It's also bonded to a hydrogen. Does it steal electrons from the hydrogen, or does the carbon lose electrons to the hydrogen? It takes from it. So should I assign that a -1 oxidation state or a +1 for the carbon? A -1. Carbon steals electrons from hydrogen but loses electrons to oxygen, has no impact from the other carbons. This is a 0 oxidation state carbon. Now my carbon gets a -1 for its formal charge and a -1 for its bond to the hydrogen, for an oxidation state of -2. The halogen has gone from -1 to -1. The magnesium has gone from 0 to +2. There has been a 2 electron reduction and a 2 electron oxidation. Carbon has gone through the 2 electron reduction. Carbon has gone from an oxidation state of 0 to an oxidation state of -2. The mechanism by which this happens is not clearly illustrated in textbooks. So I'm not going to give you a solid answer, and I'm not going to require you to understand this, but one theory is that the 2 valence electrons of magnesium split up. One goes to bromine, one goes to carbon, and the 2 electrons of the bond also split up. Radical chemistry. Another theory is that the magnesium acts as a lone pair donor and gives both electrons to carbon, while both of the covalent electrons are taken by the halogen. Either way, 2 electron reduction of carbon. And we make this new group, which some of you already know the name of. This is called a Grignard. No, it's spelt Grignard, but it's pronounced Grignard. I think it's German. I don't like that name, to be quite honest. I will use it throughout the semester, but I would rather call this an organomagnesium halide, because it gets the name across. Yeah? Here's what I would like you guys to do. Draw me the Grignard structure for the allylic Grignard with chlorine and the vinylic Grignard with bromine. Can you show me the allylic Grignard that forms just from that structure that I've given you with chlorine as the halide, and the vinylic halide, the vinylic Grignard with bromine? I've shown you what the alkyl Grignard looks like. Can you show me the allylic and the vinylic and specify the halogen? Great. Oh, yeah, but show me the structure before the squiggly line. Show me the structure like it is in blue.
Yeah, you're just.
Oh.
Am I missing something?
This doesn't look like bromine.
Oh, okay.
That's the only thing. No, otherwise good work. Good. Don't forget that vinylic bond. Good. Yep, it'll be with magnesium. The Grignard is an organomagnesium halide. What you got?
So right now, this is the allylic structure you want us to look at, right? So
Yep. And now for a halide, don't put X. Put chlorine.
Is it just,
Perfect. Great job.
we have a question. How do you pronounce this again?
Grignard. I'll understand what you mean if you call it Grignard. This looks identical. Where's the magnesium? Right?
Can I steal one of the worksheets?
No, you can have it. Yep. What you got? Good. Great. Good. Did I see yours? Good. Did you put the halogen and then an X?
By accident.
Good. Now, I would recommend that the bond not look like it's pointing to the halogen, but that it look like it's pointing to the magnesium. Because now there is actually a repulsive effect by the halogen and the carbon. So, do you understand what I mean? The way you've drawn it, you've essentially drawn it like this, as if the carbon and halogen are still bonded. The carbon and halogen are not bonded. The carbon and magnesium are bonded. So, forget the halogen is there. Carbon to magnesium. But that's a 1 minus and a 2 plus. That's not satisfied. The magnesium also has a halogen. Do you see what I mean? Okay. It's kind of like when people tell me that an alcohol or an ether, they'll show me an ether like this, a methoxy group, where they're trying to show carbon to oxygen with a methyl off of the oxygen. They're trying to show this, but it looks like they've got a carbon-carbon bond, not a carbon-oxygen bond. Okay. Okay, good work. This is what I got from you guys. MgCl, allylic. MgBr, vinylic. Just want you to practice with all of those different combinations. Now, I mentioned that we kind of see these bonds displayed as covalent. Strange. How many times do you see a covalent bond to magnesium? Probably never before, unless you've mistakenly drawn a covalent bond to a magnesium. In fact, at the beginning of the semester, I was pounding some of you guys, don't draw covalent bonds to metals. And now I'm drawing covalent bonds to metals. So don't worry, it unsettles me too. And I will accept this if this is what you want to draw. But what is the relationship between these two? They're not resonance forms. They're not structural isomers. They're just two different opinions on how you should show it, display it. All right, I want to take a quick second to point out this allylic. If this were truly a covalent bond, then the structure of the Grignard should be pretty well locked in place. This is a secondary allylic group. And yet we know from experimentation that it can also react as a primary allylic group which is to say it might be better thought of as an ionic resonance. Isn't that just beautiful to look at? Malena?
Does that mean that we have multiple products?
I'm going to avoid having you guess with this. Yeah? But you're right. It does mean that there can be multiple products under thermodynamic or kinetic control. It's true. Nice, huh? If this were a covalent bond, it would not be able to relocate because we know resonance is the delocalization or the movement of pi electrons, not covalent bonds. You cannot move covalent bonds and have a resonance form. This appears to move a covalent bond, but actually, if it is resonance, if it is an ionic bond, then the resonance makes sense. A negative charge on one carbon in resonance with a negative charge on the other. Again, a negative charge on one carbon in resonance with a negative charge on the other. We know how to show those resonance forms. Lone pair in, lone pair out. Lone pair in, lone pair out to move back and forth. But of course, the lone pairs are not moving in and out. They're in molecular orbitals, and there is a high energy molecular orbital with lobes on either carbon and not in the middle. Amazing. Okay. Our other route. This one I'll show in red. Is to take this organohalide and react it with elemental lithium. Those of you that were in lab, you have made a Grignard before. How challenging is it to work with that magnesium? Not very challenging. Lithium, on the other hand, explodes in contact with the air. Did the magnesium explode on you?
No.
No. So it might be hard, yes, but at least it's not exploding just by reacting with water in the air. This is also elemental lithium. And this forms an organolithium reagent. Okay. No one claimed that one, so there's no dead guy to name it after. What's different about this organometallic versus the Grignard? No halogen. What else? Maybe not instead of what else. Why? On the carbon? A different oxidation state on the metal. Magnesium takes on what charge? Lithium takes on what charge? So if I have carbon bonded to magnesium, I will need a second counter ion. If I have carbon bonded to lithium, they balance each other out. Once again, we can think of this as approximately equal to a carbon ion and a lithium ion. Can you tell me what type of reduction carbon is going through? Is this a 1 electron reduction of carbon or a 2 electron reduction of carbon? A 1 electron reduction, which would say that its oxidation state changes by 1. We know that carbon started as 0. What is its new oxidation state? Is it different than last time? It's the exact same anion, right? It's essentially this, which is a -2. But what kind of oxidation has lithium gone through? A 1 electron oxidation. These aren't lining up, are they? Lithium only has 1 electron to give, but carbon has received 2? Stoichiometry's off. Something else. Where's the halogen? What hydrogen? There's no change in hydrogens. Not a bad question. But this is a CH to a CH. So it's not like last time with EAS where we had half of the reactions producing HX as a byproduct. Where's the halogen? So we have 2 issues. We have not received enough electrons from lithium to do a 2-electron reduction of carbon, and our halogen is missing, and we don't know what it looks like at this point. So to clarify, it's better that we say 2 equivalences of lithium. Each lithium gives 1 electron. Now, there's a second lithium in the byproduct, Li+, which bonds with my halide, lithium halide. If I have chlorine, I've got lithium chloride. If I got bromine, lithium bromide. If I have iodine, lithium iodide. Deal? To do that 2-electron, I'm going to need twice as much lithium as I have carbon. All right, I'm going to clear some space now over on this other side. Haley, did you get all this? All the different carbon-carbon bonds? Great. We've got one last organometallic to consider. And that is from the organolithium, something that we can make. We introduce copper 1 iodide. How do you know it's copper 1 and not copper 2? It's bonded to 1 iodide, and the charge of iodide is -1. Boy, you didn't know you were coming back to Gen Chem today, did you? Iodide is -1, copper must be +1. Here's the product that I get, and I showed this to you guys on your worksheet. But we can actually rewrite this as, I'm going to draw it on its side, and I'm going to put it in parentheses. 2. This is bonded to lithium. This is bonded to lithium. What would you name this? This is called a cuprate, or maybe better called a diorganocuprate. Or because it's balanced by lithium, it might be best to call it a lithium diorganocuprate. But it's also called Gilman, after a dead man. So the Gilman reagent, the cuprate, has copper 1 bonded to 2 organo groups. What's the charge on that organo group? -1. Because we should say that that bond between carbon and copper is owned by carbon. So those electrons are really carbons. That's a negatively charged carbon. It's the exact same organometallic, or the exact same organo group. Okay, so -1, -1, and this copper had charge +1. So what is -1, -1, and +1? -1. Which is why lithium is here to balance out the charge. Okay, pause. I'm going to need 2 of these organolithiums in order to form 1 cuprate. Do you agree? I need 2 equivalences of this carbon bond to bond to that copper. but I only have one lithium. Where's the other lithium? With the iodide. So we have a byproduct again, lithium iodide. Stoichiometry is not accurately shown here, is it? If we were to accurately show the stoichiometry, we would say 2 equivalences of organolithium react with 1 equivalence of copper iodide. I hate to break it to you, but most people consider this to be the stoichiometric 1. So we're not going to write this as 2. You'll often see this as 1 to 1/2, which I don't like how it looks. And the reason I've written it in green is that I will accept it as long as you say copper iodide. You don't have to indicate that it will be half an equivalence of copper iodide. But this is how it's often written, 2 to 1, but actually written 1 to 1/2. Deal? Haley?
So would it be wrong if I say it was 2 to 1?
No. But a lot of times you will form the organolithium as a precursor to the cuprate, and you're showing the organolithium as a 1 to 1 synthesis, which means your stoichiometric amount here is already assumed to be 1. So how do I now change it to say I've made 2 equivalences of this? I've only made 1 equivalence. I'll use half an equivalence relative to my organo group. Okay. These are our organometallics, and they play very different roles. I want you guys to think of these organometallics as 2 groups. 1, strong nucleophiles. Grignards and organolithiums. You may think of them as interchangeable. If I say the correct answer is a Grignard and you provided an organolithium, you have provided the correct answer. Does that make sense? If I show on the exam answer key organolithium and you provided a Grignard, that might have been the exact combination I just said, it's correct. Right? The only difference is, do you want to go into lab and work with magnesium, or do you want to go into lab and work with lithium? That's it. Okay. Well, and that's not really it. It does come down to application, but for the most part, on paper, they are the same. Then we have moderate nucleophiles. And that's our cuprate, R2CuLi. There is another important aspect here, a difference between the two, and that is main group elements, magnesium and lithium. Their valence shells are S and P. So they do chemistry very much the same way carbon, nitrogen, and oxygen do chemistry. Copper, its valence electrons are D. Do you know why I didn't show this to you as approximately equal to anion on carbon? It's because carbon really does covalently bond to copper. Actually, it used to be referred to as a dative bond, but it is as strong as a covalent bond. This is accurate. This is not. Copper can actually bond to more than just 2 things. Copper can bond to up to 6 different things at a time, an octahedral coordination center, which means that copper can do things that the organolithium and the organometallic cannot. It's able to break and form bonds that other groups are not able to break and form. And unfortunately for us, we're not diving into the transition metal chemistry in this class. We could, but we won't. Some people do, but we won't. So we're not going to pay attention to how copper is able to do things that magnesium and lithium cannot, but it is because of the d orbitals that, that copper has. All right, so here's what I would like you guys to show me, and then as we go into this break, show me an alkyl halide, an aryl halide. Show me an aryl halide forming a cuprate. Let's rejoin at 6:09, 6:10. Okay, Ozzy, I have some bad news. My computer is telling me that it's going to restart and I can't stop it. So I'm afraid this Zoom call is going to end in like a minute and a half. But to answer your question, you're talking about the 1,3 relationship between allylic isomers. And it is directly bonded to the carbon. It is not directly bonded to the carbon. It's shown as covalently bonded. It should maybe be thought of as ionically bonded. Once this restarts, I'll try to log back in so that you can get back on. Sorry. Trying to do some Zoom.
We heard her talking.
Oh, you did?
Yeah.
Oh.
What is that?
Maybe I could set her down by you guys so you can hear her.
Yeah.
She says, no, I'm just talking to myself. Uh-oh. Not enough organo groups. Oh, I see it now. Never mind. Sorry. I didn't see the one on top here.
Oh yeah, I ran out of room and this is a big.
And that's where you could add parentheses and just put a subscript 2 instead.
Oh, duh.
Good. Yeah. I don't like the covalent bond that looks like it's pointing at the lithium.
So fair.
Did you think of anything to add to that list? Did you find any that weren't on that list? Why don't you pick a halogen to show me? Just so that you're used to. I won't accept X's on like unit tests and exams. I don't like it. So I want you to be comfortable with showing halogens.
You guys don't have elimination in acid.
Oh, that's interesting. I guess it's because I did put on the board carbon-carbon as a single bond. But you're right, this is a good way to form a carbon-carbon double bond.
Okay. Wait. It is looking at forming double bonds, right?
No. How do we form carbon-carbon single bonds? How do we begin that connection?
Oh, I see.
By the way, Jackie, you had brought up radical reactions. When we do radical halogenation of alkanes, we start with, say, methyl cyclohexane. We abstract a hydrogen and we leave behind a radical. Now, if 2 of those carbon radicals happen to exist near each other and run into each other, they can actually form a covalent bond, which is carbon-carbon bond formation. although it's typically not the desired product. And I said that, but that's not always true. Polyvinyl chloride often begins with this radical reaction where one carbon will then polymerize with another carbon. I'm showing this all happening at once. That's probably not a good way of showing it. There are radical intermediates. But that's a carbon-carbon bond, carbon-carbon bond, carbon-carbon bond. And it gives a polymer, many units bonded together, with new carbon-carbon bonds. It gives polyvinyl chloride, also called polyvinyl chloride, PVC, like plastic piping. Say what? What I'm doing a bad job of is I'm showing that these are all reacting at the same time when in fact it's probably more like a radical forms and then reacts with another carbon and then another radical forms. So that is carbon-carbon bond formation via radicals, but not a reaction we looked at in OChem 1. But you said you had 8, and we named like 4.
Well, you said what was in class, and most of them were 2.
Right, right.
So we got.
Big brain cons.
So starting up here, include file, electrophiles. She mentioned one of those.
Good.
There's the SN2 that you mentioned with cyanide.
Yep.
There's the other one that we're learning now that we didn't do in class.
Right.
I don't remember that, so I'm thinking we never went over that.
Enols we'll do at the end of the semester.
Okay. And then they got like pi bonds reacting with carbocations, which yeah, that one could work. There's the radical. There's coupling, which we haven't done. Pericyclic reactions, I mentioned that one.
Coupling we won't do either. You'll notice like all the couplings are named after people.
Is there a John?
No, I don't know, to be honest. I got so upset about all of the coupling reactions and like how hard they were to remember just based on these random people's names that I like adamantly avoided ever naming them or learning them. And maybe I shouldn't have done that, but. All right, so it's still updating. Maybe you could flag me when it's done updating, and that way I can log in. Oh,
Hey, how you doing?
thanks, Andy. So, Andy, could you tell by the language in my email that I didn't realize who it was?
Well, yeah, it felt very formal. I was like, I feel like.
Well, and then I saw your reply. You put like 8 Y's in there, and I was like, who is this? And then I was like, oh God, it's Andy. This is not the first time that we've had an email exchange like this, where I'm like, I don't know who you are, but please just reply, whatever.
That's so funny.
So funny.
I did. So funny.
All right. You should have come up with something that looked like this, or if you don't hate yourself and you wanted to make it a little bit easier, then you could write it like this. You know, I should take back what I said. You don't have to hate yourself to draw it like this. You're just being incredibly thorough. In fact, I say that sometimes with like lone pairs. Don't show them all. Why would you do that to yourself? And yet, that's one of the best ways to get out of showing lone pairs. It's to show all of them all the time and get used to all of them so that you know which ones you can avoid. So I think it's a similar situation here. Should we talk about how we use them? Reactions with organometallics. So what have I represented there in the middle of this worksheet at the bottom? RM. Organometallic. Exactly. Doesn't matter what kind. Did you say it might? It might. For right now, it can't. So until I say except or especially with, for right now, we're saying Grignards, organomagnesium halides, organolithiums, and lithium diorganocuprates, also called Gilmans, all can do these reactions. The first one I want to show you is to the right, where you can see that we have made a bond to a new carbon group. Thanks. Am I saying it has to be that carbon group if you're going to make that carbon-carbon bond? No, I just didn't really want to show R to R as the product being formed, so I wanted to give you an example, but I want you to recognize that this is really just any SN2 reaction. SN2 on a primary alkyl halide. Alkyl halide rather than vinyl halide or aryl halide, because that's where SN2 is allowed, alkyl halides. SN2 does not happen on the vinyl halides or the aryl halides. But sometimes you will see this on secondary alkyl halides. The challenge with secondary alkyl halides is that they're more substituted, and this reagent is a very good base, so it may just run elimination instead of substitution. What would the reagent need to look like if this is the bond I want to form? Well, I like to count through my nucleophilic attacks. R is my nucleophile, so that's carbon 1, and R is going to bond to carbon 2, which continues on to 3 and 4. 3 has a methyl group coming off of it. So I want to have a reagent that has carbons 2, 3, and 4. And I want to have a reagent where 2 has a good leaving group. Why do I want that leaving group to be on 2? That's where carbon 1 is going to attack. That's where my nucleophile attacks. So I'll put a halide, chlorine, bromine, iodine, wouldn't matter here. Any of our reagents can do this. If I go straight up, we see that we've made a bond to an aromatic ring, not SN2. This is SNAR. What's another way we can say SNAR? SNAR. What's another abbreviation for SNAR? NAS. That's the distinction. It's not SN2. This has a negative charge on the ring in the intermediate before elimination kicks off the halide. So what do I want my reagent to look like? Well, again, here's carbon 1, and I want carbon 1 to bond to carbon 2. So I just need, in this case, carbon 2 needs to have a halogen on it. What might improve this reaction? Put an electron withdrawing group, ortho or para, to the halogen on the ring. That's going to decrease the activation barrier, stabilize the resonance intermediate, and make it easier for this reaction to proceed. Okay, this last one to the left does have an exception. Our Gilman reagents are not typically used here. They're more moderate nucleophiles, and this reaction requires a stronger nucleophile. You can see that in our product. We've formed a bond to an alcohol carbon. Is it too many carbons? Oh, thanks. Doesn't really matter, but I appreciate that. So here's carbon 1 again, our organometallic carbon, our nucleophilic carbon, and it's attacking carbon 2. You guys understand why I'm mapping the way I do? I know what I have in the product. I need to try and dissect that apart to look at what I need in the reagent. So I need 2 and 3 to be on a carbon chain. But what is going to happen to carbon 2? What does carbon 2 have in the reagent that leaves it with an alcohol in the end? Before I give you the answer, I do want to take an aside. Organometallics as, I think I'm going to do this down below this. Organometallics as aggressive bases. Have you ever heard that word before? Aggressive base. What I mean by that is the energy released by an organometallic taking a hydrogen is so extreme it can ignite the organic material around it and start combustion. In fact, this happened more than once when I was in graduate school. The labs across from mine were working with a reagent. This is often called in-Bewley. And taking that in-Bewley and putting it in the presence of things that are even somewhat okay at donating their hydrogens results in a strong acid-base reaction that releases a ton of heat. So let's look at this in the presence of an alcohol. I think you guys will realize, or you'll agree, that water is essentially inorganic alcohol. It has a very similar pKa, very similar ability to act as an acid. So water or alcohol here, same effect. This in-Bewley just becomes butane, which means the alcohol has acted as the acid, the carbon has acted as the base, and I'm left with lithium alkoxide, ROLI, or LiRO. I can't decide which way I like to see it written better as. You guys okay with that? Those are the same thing? Sweet. Okay, well, this could be a reversible reaction. Acid-base reactions are often thought of as being in equilibrium. So let's think about the equilibrium. Here I have an sp3CH. That has a pKa in the 50s to 60s. Good acid or bad acid? Bad. Like, not, really shouldn't even be thought of as an acid. The only reason it can be thought of as an acid is because it has a hydrogen. That's the only reason it can be thought of as an acid. Do you agree? Alcohol, pKa, in the teens, 15 to 18. Good acid or bad acid? Yeah, moderate acid compared to the alkane, incredibly strong acid. This equilibrium has a difference of 10 to the 35 favoring the products. That is much, much larger than Avogadro's number, right? So for every one in-Bewley molecule left over, you have 10 to the 35 molecules of butane. That is essentially nothing. Okay. So if you need to use it as a base, not a bad base to use. In fact, there's no base better than in-Bewley. But if you're not trying to use it as a base, it better not be in the presence of something acidic. Otherwise, it will cease to exist. Is this a nucleophilic carbon? No, this is not nucleophilic. It's also not electrophilic. It's really just inert. So if I want to preserve my nucleophilicity, I need to avoid any sort of acidic condition. And this will be something that we'll hit on a few times throughout the semester with these reagents. It's great if you need to use it as a base, but if you do not want it to be a base, you must avoid anything acidic. So, I want to make an alcohol. Could there have been an alcohol in the intermediate? For instance, we looked at alkyl halide, aryl halide. Could I look at that being my reagent? It's got a halogen that can substitute, right? The carbon just has to go bond to that carbon and kick off the halogen. This is not something that's taught a lot, or maybe will even make a lot of sense, but acid-base reactions forming bonds to hydrogen, those happen much, much faster than any other type of reaction. So if acid-base can happen, acid-base will happen first. Can acid-base happen between my organometallic and this reagent? Yes, absolutely. Will acid-base reaction happen? Yes, absolutely. So this cannot be my reagent because the actual product would be ROLI. Right? After Rn takes on a hydrogen, it just becomes R. I mean, I guess I could show it RH, but now it's just an alkane. So what do? To make an alcohol, we will run acyl addition. Do you guys think I ask enough questions in this class? What is an acyl group? Ketones and aldehydes? Milena?
It's like a ketone group next to a halogen.
A ketone next to a halogen. So I think what you mean by ketone, which needs carbon on either side of the CO double bond, I think you mean carbonyl. And so you're saying the acyl group is acid chloride, because we saw that with acylation, right? Acylation was taking an acid halide and putting it onto a ring. But it doesn't have to be limited to the acid halide, because we also looked at acyl reduction back in our benzylic reactions. We had ketones and aldehydes, and we reduced them. And I think I called them acyl reduction, but maybe I didn't. So the acyl group is the same thing that you should think of as a carbonyl group. Now we've just got two different terms for them. Deal? Aldehydes, ketones, acyl groups. Acid chlorides, acyl groups. Carboxylic acids, acyl groups. Here we've got acyl addition. Okay, now we know an acyl group is a carbonyl. What is addition telling us? I'm going to add across the pi bond. There's the pi bond, CO pi bond. I'm going to add across it. What am I left with after I add across the pi bond from CO? Just a CO single bond. Yeah? But I can't have organometallics in the presence of a base. In the presence of an acid. So where is this hydrogen coming from? Here's the reagent that we'll need. We'll need carbon 2 to be an acyl carbon. Why? Because that's the alcohol carbon. That's where the CO bond already is. 2, 3. In this case, the acyl group is an aldehyde. And when R bonds to that aldehyde carbon, now it has 2 groups bonded next to it. One on the left, one on the right, and it just has the CO single bond. But this is not enough. There's no hydrogen that's being brought in here. So where does this O get a hydrogen from? We have to introduce an aqueous workup. So we're going to write this as first, add the acyl group. Second, I'm really running out of space here, so I hope you don't get lost. Second, H3O plus. H plus is another way that we can write this. H3O plus, or even just acid workup. A lot of times you might see that in different places. Acid workup, that's all that we're saying. Great. So really there's 4 things that we can do. We can do SN2, we can do NAS, and we can do acyl addition or acid-base chemistry. But I want to point out that the Gilman reagent is not a strong enough nucleophile to do the acyl addition. It just doesn't have that get up and go to bond to the carbon of the carbonyl. So we won't use it for that purpose. We'll use organolithiums and organometallics. I have one more reaction to show you from the organometallics. I said organometallics, I meant organolithiums. One more reaction from organometallics to show you. And it is a specific type of substitution that we have not seen yet. And that is, I think we're going to have to erase this, using the cuprate only. I'm going to add a little bit to this. This is trans. It's a trans alkene, and it will stay trans. And by pointing that out, what I'm highlighting is that stereochemistry of alkenes is unaffected by this. Okay. Only Gilman can do this. Does it look like substitution? Yes. Sorry. Is it substitution? Yes. Does it maybe look like SN2? Sure, I can see how it might look like SN2, but we know that SN2 does backside attacks. If you were to do a backside attack on this carbon, then the methyl group should shift over and it would be a cis alkene afterwards, not a trans-looking alkene. Yeah? So this is not SN2. Because also, SN2 is forbidden on those vinylic halides. SN2 can't happen on sp2 hybridized carbons. Instead, this is a strange property of the copper. the copper is able to actually separate out the alkene from the halogen. It's able to bond to both of them, separate them, and then slip together that alkene with the new R group. I know you might be itching for that mechanism, but that mechanism is not what's important in this class. And to be quite honest, not typically shown with normal arrow pushing. But super cool, huh? The copper is able to pull it apart, piece back together other pieces. Magnesium can't do that. It doesn't have d orbitals to accommodate that. Lithium can't do that. All right, so we've got SN2, NAS, acyl addition, and then this vinyl substitution. If you want to give this a name, the best name would be vinyl substitution. All right, I have another worksheet that has some practice problems on aromatic substitution. And this is the worksheet that was already uploaded on Canvas this morning called Organometallic Synthesis.
Is that an R or an X?
On the bottom?
Yeah.
You tell me.
R?
Right.
Okay.
Yeah.
Yeah.
Sorry about that. I don't know how to clarify it though. Just have to rewrite it. So using some of your skills on multi-step synthesis, I want you guys to think about how these reactions on the front can be done. Oh, there's nothing on the back anyways. How we can perform these reactions on the front to get the final products. You're welcome. You're welcome. You will need to use some OChem 1 knowledge here. Things that we reviewed in the first half of in Unit 1. No, never mind. I was going to say something else about acyl addition. We're going to focus predominantly in this unit on aldehydes and ketones here. But in Unit 4, we're going to come back to look at other acyl groups. So for right now, aldehyde and ketones, but not forever. Okay. Do you know what? I think this worksheet will be how we wrap up class today. So we're going to be working on this for the remaining 15 minutes. Ask questions, and in the last few minutes, I'll go through and solve some of them on the board, show my thought process for you. What will this react with?
A halogen, so I need to do free radical bromination.
Nice. Now, free radical bromination is not HBr. This is if we have like an alkene, and I want to put H on one carbon and Br on the other, especially if I want to reverse Markovnikov's rule. To slap it right onto an alkane, I just need elemental bromine and light.
Oh, it's just BR
Mm.
2.
Mm-hmm.
Okay.
Good.
Do you want like this?
So this is good. Now you've made the organolithium, and now you've made cuprate. But how do I get a new carbon chain? Do you agree? After step 3, I'll have R2. Here's R. R2CuLi. But that doesn't actually give me a new group, does it? A new carbon group. So you got one step left. And to be fair, you don't need this step. You could do it from a cuprate. You could do it from an organolithium. Do you see what your target is? Maybe it'll help if you draw the intermediates that form so that you can kind of visualize what reaction you need to use. Hi, Lily. Okay, so this would work on an aromatic ring.
Oh, that's not an aromatic ring.
Yeah. So first hint is, what functional group do you have at the start? Okay, some people say it's not a functional group.
Yeah.
Alkane.
Oh, yes.
And what is the only thing you can do with an alkane? Other than burn it. Good. Now do you see where you are up there? You're at Rm. And where do you want to go? Do you want to get onto an aromatic ring? Do you want to make an alcohol? Or do you want to bond to a carbon chain? Great. So here's your nucleophilic carbon, carbon 1. Here's your electrophilic carbon, carbon 2. You agree? This carbon here needs to bond to that carbon. Okay. So our first step is, what can we do with an alkane? There's very little we can do with an alkane, but I like the carbon group that you guys have provided. Eventually, I'm going to need a 2-carbon chain with 1 leaving group. So this will come in handy, but not yet because I have no nucleophile. Not quite, but I see what you're thinking of. Well, the alkane doesn't go through a lot of reactions. So thinking back to OChem 1, what can we do with an alkane? If you've got your notes even from our OChem 1 review, you'll notice that there's just one reaction with the alkane. Do you guys find it? Radical halogenation. You place a bromine right onto the carbon chain, but it goes somewhere specific. The most substituted carbon. The reagents, Br2. To run radical halogenation, I need elemental bromine, Br2, and I need light, which will start the radical reaction. That's step 1. This is a multi-step synthesis. I don't know if that was clear. So you're gonna use at least 3 reactions. My advice is draw the intermediates as they form so that you can think about how to use them. Good start.
With the organometallic, can we use any metal?
Yeah, I mean, it depends on which way you want to go. If you're trying to do acyl addition, don't use the cuprate.
Okay.
But if you're doing these other ones, yeah, you can use anything.
But in our products of the reactions that we've seen, the metals are involved in the molecule.
Yeah,
So how do we get rid of it?
there'll be a byproduct. Hey guys, let's take a quick analysis on some of these byproducts, because I think not looking at the byproducts may have been a little confusing. Let's say that I had used a Grignard organomagnesium halide in this substitution reaction. My byproduct would be MgX2. The magnesium is one of the byproducts. If I had used organolithium in my aromatic substitution reaction, my byproduct, lithium halide. The metal is now waste. What about here? What are my byproducts? There's more than one. Actually, it's just organocuprate, carbon to copper. You know how I had two equivalences of that carbon group? Say goodbye to one of them. In terms of wastefulness, the cuprate is fairly wasteful. For all of that organic material that you created to bond to copper, you only get to utilize half of it, and the other half goes to the waste. What's the other byproduct? Lithium halide. So cuprate, definitely the most wasteful of any of these reagents, because half of your carbon group ends up in the waste with the copper. But in all of the cases, the metal will end up as a byproduct in the reaction. That was a good question. Did that help to answer it? Okay, so great. Now think about how you can go from here to something that helps you get here using a reagent like that, or work backwards. What could you have had prior to this using this as a reagent?
Can you also use like a Cl2 for this?
Yes and no. Cl2 is very reactive as a radical, and Cl2 will go all over the place. Bromine is more selective. Bromine will always go only to the most substituted carbon.
I have two questions. For this one, would this be kind of the process you're using of like putting in a halogen and then using like Na? Or am I...
So you've got this idea, here's your organometallic. The problem is we aren't looking at any organometallics that use sodium.
Okay, so this is considered your organometallic that I would then be combining with one of these.
Well, no, you've created an organometallic.
Okay.
You have presented an organometallic reagent, but when we see sodium as the metal, it's usually sodium to a deprotonated alkyne, or it's sodium to cyanide. But let's assume that it works. The main issue here is that your strong nucleophile is trying to do SN2 on a tertiary carbon.
Oh, that's
Tertiary carbons don't do SN2. They do SN1, but in the presence of something that's a good base, they do elimination instead. So I need a primary carbon, which means you've got a good idea. Let me substitute the halogen on that tertiary carbon, but it won't do substitution. So we'll have to use that carbon not as the electrophile, as the nucleophile.
Okay.
So how do I take this and turn it into a nucleophile? I'll give you a hint. If you need to prepare organometallics,
But if you use magnesium, aren't you just trapping yourself with the magnesium?
no, not really. If I use magnesium here, I essentially get that pair of electrons back on the carbon. Now I have a nucleophile. That carbon will now want to attack somewhere else. What carbon will it attack? Well, this one. But now put a leaving group on it instead of sodium. Another thing I want to point out, we won't use chlorine for this.
I heard you talking them into
Okay.
bromine.
Yeah. And we would need light HNu.
Okay.
On its own, it won't become radicals quickly enough.
I was gonna ask you, how do we use light in a reaction, like in a lab? How do we?
It's ultraviolet light.
Ultraviolet. Okay.
So you basically have a black light, and you just shine it over the reaction, and the electrons absorb that ultraviolet light. HOMO electrons move into LUMO orbitals, which typically breaks a bond.
Oh, okay. I was just curious.
Yeah, totally. Okay, so swap that out for bromine,
Yeah.
and then think about how to make it into a nucleophile. What do you think, James?
So,
What you thinking?
I'm kind of lost.
Yeah? What can we do with an alkane?
So within the context of this,
We could burn it, but that's not helpful for us. So I want to preserve my carbon chain. I can't do hydration. I can't do alkene addition. I can't do elimination. The only thing I can do is substitute one of those hydrogens for a halogen, but not easily. I need radical chemistry to do that.
would we be subbing a hydrogen attached to this carbon?
It's a good question. We can't always control it, but if we use radical halogenation, Br2 in light, Br2 will selectively go to the most substituted carbon.
So then would it go together?
That's right. So you can create an alkyl halide. Now that you have an alkyl halide, you can make an organometallic. Now that you have an organometallic, you can do substitution. Oh, I forgot we got out in 1 minute and not at 7. Sorry. All right, let's talk about number 1. In reaction number 1, we have nothing to react with. So we take the most substituted carbon and we turn it into an alkyl halide. We do this by radical halogenation. Why is it the most substituted carbon? It's because the radical is most stable at the most substituted carbon. Now I can turn this into an organometallic. It does not matter which one, but cuprate would be wasteful and an extra step. So organolithium or Grignard is a good option here. Now this can act as a nucleophile, and all I need is a 2-carbon electrophile. Carbon 1 is the tertiary carbon, attacks carbon 2 and 3, and gives me that new carbon chain. I do want to point out one thing that was a good thought, which was when I have this tertiary alkyl halide, can I just attack it with an organometallic? Can I introduce an organometallic and do SN2 here? No. Tertiary carbons are too sterically strained for SN2. It has to be a primary or a secondary alkyl halide. So let's show it. If I had introduced this as my organometallic, the product that I would have gotten is probably this alkene. Not great, because I wasn't going for an alkene. If I want to make that carbon-carbon bond, I need the tertiary carbon to be the nucleophile, and I'll attack a primary carbon. Should we start off with the other two tomorrow? Because I don't have time to give them to you today. But what I will say about both of them is they will involve intramolecular reactions. You will need to prepare it to react with itself. Okay, Thursday's class will open with those problems. Okay? Work on them. Try to solve them. Have a good night. Thank you for your time.